Hello everyone, my name is Tang Tianwen. My nickname is Victory. My partner is Xiao. Thanks for joining this speech. Let's start the journey of Breakout the Western world. I work at 360 Security Wildcat team. I major in virtualization security for 2 years. I've found several critical bugs on VMware products and Hyper-V. Here is my partner Xiao. He worked at a 360 Security Wildcat team too. He has won several virtualization escape challenges, including Workstation, ESXi, VirtualBox, and QEmail. Next, let me finish this speech. First, I will introduce virtual network device in VMware Workstation and ESXi. Next, I will introduce the primitives during exploitation. Then we show two examples with these primitives. Furthermore, we will show a demo of escaping from ESXi. At last, we discuss what we learned and what is new in newest workstation. In this part, I will talk about virtual network architecture and its attack surfaces. Device architecture. Workstation and ESXi have similar architecture, so I don't make a distinction unless it's necessary. Look at this picture. We call a virtual machine as guest, the real machine system as host. Call the process in host which running a guest as VMX process. Each guest network driver communicates with the virtual network device directly by I/O operation, including I/O ports and I/O memory. And each guest is running in different VMX process. As you can see, virtual network device filters data from guest driver and send it to physical driver. Here is an abstract picture of VMX process architecture in VMware Workstation. There are 3 different virtual network devices shown in this picture. Each device has its own command analysis function and filter function. They use a common transfer function to handle network data. ESXi handles data in kernel instead of a user process. Guest driver use I/O operation and web map to translate commands and data to network device. So we know the bugs may exist in virtual network device when it handles data and command from guest driver. Obviously, there are 3 attack surfaces in virtual network device. First, if a virtual network device handles guest command data incorrectly, it will cause a problem. The case of escaping from workstation belongs to this. Secondly, if a virtual network device handles guest physical memory address incorrectly, it may also cause a problem. The case of escaping from ESXi belongs to this. Thirdly, if a virtual device doesn't check common data completely, the common data may transfer to host kernel, which may let host crash or worse. I have found a bug exists in VMCI host driver. It may be published one day. When we find a bug, we should exploit it. But before we do it, we have to understand how a WMX process accesses guest's memory. Then I will introduce a way to heap spread, a way to read and write data between guest and host process, and a way to bypass CFG on Windows 10. Guest memory. At first, let's find out where the guest physical memory is. Look at the picture. The yellow rectangle represents process memory. Purple rectangle named WebMap represents guest physical memory. WebMap is a map space in process memory. In this picture, guest system can access WebMap directly, but WebMX process needs to translate a guest physical memory address into process memory address. If it wants to access WebMap. In my thoughts, if the physics and size is illegal, address translation function should return fail. But, however, WebMX tries to allocate a 4K heap or an array to store translated address for each page frame number and return success. Let's see the code. On left is a structured definition of WEM address trend. This structure is related with the address translation operation. On right, WEM address translate is a function for translating guest physical memory address to a process address. Phase2Vert is going to check range of physical address and size and return the process address by adding WebMap offset with a given address. If Phase2Vert runs success, it will assign the result to field Tang and return success. If else, if Phase2Vert runs fail and the nums is equal to 1, it will try to allocate a 4K heap, or after 10 times fail, it will assign this memory to field Tang. We call this memory as H1. It's an important characteristic to leak data from host process to guest. When process handles a buffer from guest, if we can confuse the range of a translated buffer, we can overflow read or write process memory instead of WebMap. If the num is bigger than 1, it will allocate a buffer to store result for each page frame number, and the array pointer will be set to field 18H. Once the guest's memory has been handled, function WebMap address translate free will be called. In this function, it will free memory allocated before. Now let's look at an example. Look at the upper part of the picture. If we give a physical address and size like this, the given range is bigger than WAM map, so WAMX will allocate a 4K heap. Look at the lower part of the picture. If the sum of page offset and size is bigger than 4K, it will allocate a page array stores at here. So now we know how WAMX translates address from guest. Next, we need to discuss exploit primitives. Heap spray. To make our exploit stable, we need to heap spray for heap layout. The easiest way is to use SVJ shader buffer. We can decide its content and size, and we can release at any time. However, we can't change its content after the memory is allocated. The details of sending a SVJ comment, you can watch this proposal. They made a great work to explain the details, so we don't need to tell it now. SVJ has a mob structure that allows guests to transfer data between two mobs. The field, as you can see, the field of guest buffer stores the result pointer from translation function. So if we can overflow the size field of this structure, then we can overflow read and write between guest and process memory by this SVJ command. In WMX-3 module, it's a default network device used in ESXi. We can use MF table to write data to a heap. We can control blocks data after the memory is allocated. And we can also control its allocation and release. SVJ GM buffer is a MKS heap. MKS heap is a special heap with an extra heap header. The header field looks like this. It has a field named header size. When freeing a MKS buffer, it calculates the real heap header by subtracting buffer address with the header size. So if we overflow a MKS heap header size field, we can free another heap. One way to bypass CFG is to change stack return pointer. So we need to find a skill to leak stack related address. After we can read and write everywhere, we can control SVJ function table. And let it call a special function which can set R9 from a global pointer, which we can control its value. Then let it call a short function like this. In this function, it will copy data from RCX to R9. And this SVJ call function, it uses a stack address as argument 1. So RCX is point to a stack address. So we can link stack pointer to guest. Now let's start a real practice. ESXi is a Linux-like system, so we can assume that it's a Linux system. A funny exploit steps based on Linux system's heap features. The bug exists in WMX.3 module. Let's see this translate function. If the sum of phases and size is bigger than limit, it will return 0 without reset the data of this variable. And in WMX3IO handler, it calls this function without check function's result. And then it will call a free function. In this free function we mentioned before, it may free a heap from stack variable. So this leads to an initialized bug. To exploit, we need to transfer it to an UF bug. Here is the details. Firstly, we give a wrong physical address like this. Then the translation function will allocate heap with size 0x60 and assign it to field 18H, and the heap will be freed in release function. Secondly, we allocate a MF table with size 0x60, and the heap should occupy the same space, because the space should be the first chunk in free list. Then we trigger the bug. It will free the pointer stored before, which points to MF table now. So we get a dangling pointer of MF table. Fourth, we allocate a GMR buffer to occupy the freed MF table. Then we allocate a mob with a 4K heap. With our heap control, the heap layout should look like this. Then we change the MKS header from this to this. And when freeing a GMR buffer, the function gets the heap address by minus MF table's address with header size 0x3010. So in fact, it doesn't free GMR structure. It frees the mob's heap block. Thus, we get a mob that points to a free memory. Sixth, we allocate a shared buffer to pad that 4K block, and the size should be like this. Then it will split a OX60 whole block. Then we allocate a mob2 structure. We allocate a new mob structure. We call it mob2, and it should be put at our hole. We let mob2 point to H1 because H1 is an early allocated block. It should have a lower address in memory process. 7th, we use mob1 to change mob2's size field, so we can read and write host process data after H1. We can use SVG command to copy data between these two mobs. ESXi doesn't have CFG or railroad, so we can control its function pointer directly. We just need to find a dynamic call with control arguments. Here is a sample of control IP I used before. In SVG draw data draw command handler, it will set v2 from a global pointer. Because we can read and write everywhere, so we can control its value. Then it will call this function, and this function, and this function. And the RDI is equal to A1. So we can control IP with our arguments. Because RDI is the first, it stores first argument or a caller in a next system. So we control the first arguments. Let's start another case. Let's say difficult the first time, easy the second time. Here is a bug function. I had some unnecessary codes, so don't confuse with the code logic. Data of memory is controlled by guest. At line 81, variable v17 is equal to variable 23, and v17 is a short, and v23 is a integer. So there is an integer truncation problem. And look at the line 91. Rest size is equal to variable v23. v17. If the value of v23 is bigger than OX10000, then v17 must be smaller than rest size, and per size will be assigned with v17. So the rest size must be bigger than 0. So memory copy will be called, and it copies the data from map to its end. And so here is the heap overflow. And there's another way to overflow data with a given offset. It's not shown in this picture. Because Windows has LFH, so
It's a problem to arrange heap layout, but it's not impossible. Firstly, we allocate many mob blocks like this. It will fulfill a LFH block. And then we free several mob structures. So there are several holes freeing blocks in a LF chunk. And then we trigger the bug. If we are lucky, the mem and the mob should be adjacent, and it can overflow a mob size field. Thus, we can leak information from host process memory. We let all mobs point to H1, and the data after H1 should be leaked from mob. Then, after leaking process-related address, we overflow again. We change mob's pointer. Let it point to mob list. Mob list stores the address of mob structures. It's in our data segment. Then we fake a mob structure. Let its guest buffer field point to SVJ FIFO command scratch space. It's the SVJ command buffer at .r data segment. We can use this SVJ command to change its data. So we can fake any mob structures we want.
After previous steps, we can control a mob structure. It means we can read and write everywhere with two fake mobs, but we don't know the translated address of guest's memory. So we need to leak where map offset to guest firstly. To achieve this, we let a mob point to the address where stored where map offset. Then we use surface copy and surface DMA command to leak data from a mob to guest's physical memory. After this, we know what is the translated address of a guest memory. So we can fake two mobs. One points to somewhere we want to read and write. One points to our guest's memory. After this, we can read and write everywhere now. As mentioned before, we use this skill to bypass CFG. Here is the demo of escaping from ESXi. Now you can see I created a new file named T2. It's a root privilege. So what we know, programs may be careless about the returned function results.
Creating an extra heap header without encoding is not a smart idea. Manufacturers should add modern mitigation measures to their products, like ESXi should add CFG or railroad. VMscape is not as hard as we expect. Virtualization security is still a serious problem at present. We should be careful. New change. To avoid to abuse mob structure, VMware Workstation 15.5.x stores mob structures in .r data segment instead of allocating a heap. But other primitives still work, and it's easy to find a similar structure in SVGA. At last, thank you.